let us look at the fourth lecture, understanding the relationship between color and constitution. So far we have dealt with the history and then the light and its interaction with the color. Then thirdly, we looked at the classification of the dyes, both synthetic and natural, in terms of their structural details, and now we will see how color and structure is related in this present lecture. Electromagnetic radiation, that is, light is electromagnetic radiation, that is, it has both electrical and magnetic component vibrating in transverse wave packets or quanta. The vibration may occur in all planes or in one only plane polarized light, each plane having right and left circular vector components. We may measure the amplitude of the wave quantum, that is the intensity of the light, its frequency and or its wavelength, and then look at the color tone and its velocity in a given medium. So, all this will be now related to what color will be observed or seen. We also saw that the complementary color is generated from the transmitted light, because the absorbed light is taken up by the material. Now, if we try to have a recap of color, chromophore and auxochromes, the carbonyl and the ethylene or vinyl groups have chromophoric properties only when they are present in the molecule in multiple conjugated order. So, now you understand what is a chromophore. Thus, acetone is a colorless molecule, while diacetyl is yellow and benzyl is deep yellow, while triketopentene is yellow orange. Since it is the delocalization of the pi electron that is related to the production of color, it is evidence from these examples that such delocalization accompanies multiple conjugated unsaturation. So, for a molecule to be a colored molecule, it has to have chromophore and auxochromes, and the two put together, if they are in a conjugated system, will create color. So, that is the relationship between color, chromophore and auxochrome. Now, if we try to look at various types of chromophores, Witt observed in 1876 that colored compounds contain certain unsaturated groups which are called chromophores, and the compound containing a chromophore is called chromogen. When certain groups called auxochromes are present in the chromogen, a dye is obtained. So, a combination of chromophore and auxochrome creates a dye. The various different types of chromophores are keto group, nitroso group, quinonoid group, ethylenic group, nitro group, azo group. These are some of the common chromophores that we see in the case of dyes. The common auxochromes that are observed may be either acidic or basic like OH or NH2. Other auxochromes include carboxylic acid, that is COOH, SO3H, NR2. These groups form salts or either acids and alkalis. So, with either they will be forming a salt with an acid or an alkali. They also form hydrogen bonds with certain groups like OH of cellulose or NH2 of the wool and silk. So, a basic azobenzene has a N double bond N with two aromatic rings on the side, whereas this contains the azo chromophore and not serving truly as a dye, because it is not having enough conjugation and there is no auxochrome. But simply by adding an NH2 which is an auxochrome, you see that the conjugation extends. The lone pair on the nitrogen of the amino group at the end is in conjugation with the first ring, which is in conjugation with the azo linkage, and which is in conjugation with the benzene ring. So, you see that there is an extension, and this is a very well known dispersed dye, an example of a dispersed dye. So, the azobenzene is not a dye, but the para amino azobenzene becomes a dye. So, you understand now how the role of an auxochrome enhances the coloring property of a material or a compound, chemical compound, and from a colorless compound it becomes a color compound because of the extended conjugation. Classification, which is based on their chemical nature. Now, let us try to say, I told you several names, but I will still repeat so that you get a good idea about the relationship between color and the structure. That time we were taking classification only in terms of the structure. This indigo dye, indigoid dye is most common group of natural dyes. The dye stuff is extracted from Indigofera tinctoria, a bush pea family member. The dye was used prehistorically in India, where it probably originated. The word is derived from indican. Now, you see it has a benzene ring, it has a carbonyl group, it has an NH2, NH, and they are now connected with a C double bond C. So, that makes it a blue colored dye, because it has all the requisites of chromophore and auxochrome. Now, let us look at the anthraquinoid dyes. We just looked at the various structures of anthraquinoid, examples of madder or mungist, and we saw that how alizarin and other dyes are all having this basic skeleton. Now, this is called an anthraquinone basic skeleton. Now, different types of auxochromes, when attached at different positions on either of these rings, can produce more and more color, and the intensity of color goes up as much as the delocalization of the electrons happen, and that is related to the various functional or auxochromes that are connected to these aromatic rings. Some of the most important red dyes are based on anthraquinone structure. They are obtained both from plants and insects. These dyes are characterized by good fastness to light. They form complexes with metal salts, and the resultant metal complex dyes have good wash fastness. Now, when these aromatic rings have OH, the OH at the ortho position can chelate the metal very easily. We will learn all this in due course of time. Right now, it is important for you to simply understand what the basic structure is. Similarly, we have another category of structurally different dye, which is called alpha naphthaquinone. Alpha naphthaquinone, the best example is the henna dye, which has lauzone. Lauzone is a compound which has a very simple structure as shown on the slide. It has just one benzene ring and this double carbonyl and an alpha beta unsaturated say double bond carbon-carbon double bond having an auxochrome OH attached to it. So, you see it is from henna, which is Leucaena inermis, that is the botanical name of mehendi plant, and the mehendi plant consists of this lauzone dye, which is orange in color, and it stains the palm protein, skin protein very readily. The next category of structurally different compound is flavones. Flavone is a colorless organic compound to begin with. Most of the natural yellow colors are hydroxy or methoxy derivatives of flavones and isoflavones. It is obtained from as dust on the flowers and seeds of various primula species, in buds of various varieties of poplar, in yellow dahlias, in weld, that is Roseda luteolia, and dyer's bloom, that is Genista tinctoria. So, these are the various sources of yellow dyes, but the basic flavin ring is a colorless compound. So, what does it make you understand? I am trying to draw your attention to the simple fact that auxochromes are really required to make a conjugated molecule into a colored molecule or a dye molecule. Relation between color and constitution. Now, if one has to understand this, like the physical and chemical properties of organic compounds, there is a definite relation between the color and constitution. Benzene is colorless, whereas its isomer flavin is colored. The following theories have been proposed to explain the observed general relationships existing between color and constitution. So, there are various theories postulated from time to time in order to explain what is the relationship between the structure and the color of a compound. So, we try to learn and understand one theory after another theory to be able to understand how we came to the modern theory of color explanation. Witt theory, which is the most important and the earliest theory that was postulated, is based on the chromophore and auxochrome theory, the one which I have been explaining for a while in this lecture. In 1876, Witt put forward a theory according to which the color of the substance is mainly due to the presence of unsaturated group known as the chromophore, and it comes from the Greek word chroma, which means color, and phore means bearings. The important chromophores are C double bond C, C double bond N, C double bond O, N double bond N, and NO2, quinonoid rings, and so on. So, we just looked at the various chromophores a while ago. So, according to Witt, it is because of these chromophore groups and the association of auxochrome that makes a chemical moiety a dye, because of extended conjugation. So, there are three criteria that he mentioned: presence of chromophores, presence of auxochromes, and the third thing is that they must be in conjugation to create a greater delocalization of electrons, and only when the electrons are more and more delocalized, a colorless compound moves towards becoming a colored compound. The compounds possessing chromophores are known as chromogens. The chromophoric groups are the following two types. When a single chromophore is sufficient to impart color to the compound, then these chromophores are of the category NO, NO2, N double bond N, N double bond N, double bond N, and so on, or N double bond NO, or para quinonoid structures. This, if they are present only in one number, even then they can create a lot of color or impart color to the compound. When more than one chromophore is required to impart color, like CO, C double bond C, this can be exemplified by the example that I took a while ago. See, acetone, which has just C double bond C, C double bond O, is actually colorless, but when there are two such groups attached to it in biacetyl, it is yellow in color. So, you see that one is not enough to impart color, but when two such chromophores are present, or if there was an alpha beta unsaturated ketone having C double bond O and CC bond, then it would have been pale yellow in color. So, the more conjugation it brings in, the better it is. So, among the two categories of chromophores, the nitrogen bearing or the quinonoid ones, even if they are present in one number, can impart enough color. But in the case of carbon bearing chromophores like C double bond O or CC bond, they have to be more than one chromophoric group to create the coloration. How does it work? Since the auxochromes are capable of forming salts either with a basic or acidic group, their presence also convert a colored compound devoid of salt forming groups into a dye, which must fix permanently to the fiber. It must be fast to water, light, soap and laundering when fixed to the fiber. The permanent fixing of dye to the fiber is generally due to the formation of chemical bond between the fiber and the auxochrome. This can be exemplified by the following example. Now, auxochrome, that means, have two roles to play. One role is that they enhance the conjugation effect, or at least they participate in the conjugation effect. And the second role that they play when they participate in making a compound into a dye is in the adhesion of the dye to the fabric. So, auxochromes are very important integral part of a dye molecule. Now, when we try to look at these molecules, you see benzene is colorless, diazobenzene is also colorless, but the moment an amino group or a diazonium salt is made, diazonium chloride, it makes a kind of a colored dark yellow compound, and that is what makes that more and more presence of auxochrome make it a better dye material. The next theory that was proposed for explaining the relationship between color and constitution was the theory proposed by Armstrong, which is based on the quinonoid theory. Armstrong or quinonoid theory in 1885 suggested that all coloring matters may be represented by quinonoid structure, that is para or ortho, and thus believed that if a particular compound can be formulated in quinonoid form, it is colored, otherwise it is colorless. Some of the important compounds, the coloring properties of which can be explained on the basis of this theory are given below. So, you see, he suggested, Armstrong's theory says that all structures which can form quinonoid structures, that means all chemical compounds can become a dye if they fall in the category of writing their quinonoid structures, and if that is not possible, then they are colorless. On the basis of this theory, we can see that benzene is colorless, whereas benzoquinone is colored. So, that is how he proved that benzene, because it does not have a quinonoid structure, it has just a benzenoid structure. But the quinonoid theory is not sufficient to account for the coloring characteristics of many compounds. For example, the aminoquinone and the diaminoquinone both possess a quinonoid structure, even then they are colorless. So, if we try to look at these four structures now, benzene is colorless, but benzoquinone, that means this kind of ring with double bonds and carbonyl is a colored situation. But when we look at aminoquinone, that is carbonyl with NH or NH with NH, diaminoquinone, then these latter two are not colored. So, how does one explain that this quinonoid structure is valid? So, there it is kind of failing to explain many structures which cannot be written up in their quinonoid form. So, therefore, the modern theory came into existence, and the modern theory then talks about in great detail as to how these structures can be correlated to the various explanation of the previously explained Witt's theory and the second Armstrong theory. It has to offer something better and more convincing explanation for the relationship between color and constitution, and that is what actually has come into being, and it has been practiced. The above two theories were discussing the relationship between color and constitution and were found to be only empirical. That means, it was valid in certain cases, but not valid in many cases. The next two important theories which explain the the relationship, the plausible relationship between color and constitution require somewhat theoretical background about the effect of light on the molecule. So, this modern theory is now based on a very different concept. It is not based on what is present on the structure, but it is based on how light is reacting on that structure, and therefore, it is the effect of light on the molecule which is the basis of the modern theory to explain the difference between a chemical and a dye, to explain the difference between its color and its constitution. And the two theories that were postulated were valence bond theory and molecular orbital theory. So, from time to time with advancement, first came the valence bond theory and then subsequently the most acceptable molecular orbital theory came into existence. The valence bond theory. Valence bond theory, the various postulates of this theory are as follows. Chromophores are groups of atoms, the pi electrons of which may get transferred from ground state to excited state by the absorption of radiation, thus producing color. So, this is what we actually were trying to refer to, the fact that it has so many conjugation. Each pi bond has pi electrons, and it is the delocalization of these pi electrons which are getting transferred from ground state. Once they absorb light, they are so facile that they can get excited to the excited state by the absorption of the radiation. And so, the more number of pi electrons, the more light will be absorbed by them for exciting the pi electrons from ground state to excited state. And auxochromes are groups which tend to increase the resonance by interacting the unshared pair of electrons on nitrogen or oxygen of the auxochromes with the pi electrons of the aromatic ring. This increase in resonance increases the intensity of the absorption of light and also shifts the absorption band to longer wavelength. Hence, there occurs the deepening of color. From this, it is evident that increase in resonance must deepen the color, and actually it has been found to be so. Now, this also is based on the presence of auxochrome and chromophore, but auxochrome, how they are participating is being explained on the basis of the lone pair of electrons that are present on the nitrogen or oxygen containing auxochromes and their participation with the pi electrons. So, when the pi electrons have an influx of electrons from the lone pair of the nitrogen and oxygen, what happens is that their excitation by the absorption of light is facilitated, and that also causes deepening of color, because the more facile the excitation, the longer will be the wavelength and shorter will be the energy requirement for such transitions. Furthermore, the dipole moment changes as a result of oscillation of electron pairs. the following order has been observed for the case of excitation of different groups. If we try to look at the various roles of auxochrome, it is N double bond O which is greatest, which is less than which is greatest, and less than that is C double bond S, which is greater than N double bond N, which is subsequently less than C double bond O, N double bond N, C double bond N and C double bond C. So, this is the order of their dipole moments, and the dipole moments then is creating this excitation of these different groups. Resonance theory explains the relationship of color and symmetry of the molecule or transition dipole of the molecule, because as the number of charged canonical structures increases, the color of the compound deepens. The more the possibility, the longer the path for a change to oscillate in a compound, the longer wavelength of light will be absorbed, and therefore, deeper would be the color of the compound. So, it all depends on how many canonical structures can be written, and the canonical structures are occurring due to the resonance that is occurring between the different participation of the lone pair with the pi electrons. So, it is all classical organic chemistry based fundamentals which need to be revived when we are trying to look at the valence bond theory of understanding the color and the constitution, because everything is very systematic. If there is a nitrogen or amino group attached to aromatic ring, the lone pair on the nitrogen will participate with the pi electrons of the ring. As a result, it will have an enhancing effect. Now, if we try to look at various structures, we will also appreciate, I just took an example, I will go back to that example, that benzene, diazobenzene and this amino substituted compound. You see that benzene had only the pi electrons, diazobenzene had the pi electrons of the ring and the N double bond N as chromophore, but still it was only light yellow in color. But the moment there was this amino at the substitution of one of the aromatic ring, this amino then started the lone pair started conjugating with this ring electrons, and these electrons were participating with the azo linkage, and the azo linkage was then participating with the second aromatic ring. So, you see how beautifully this conjugation system can be explained and the various resonance structures that can be written for this purpose. Now, then came the most advanced theory of molecular orbital. The molecular orbital theory, according to this theory, the excitation of a molecule means the transference of one electron from an orbital of lower energy to that of higher energy. These electrons may be sigma, pi or n, that is non-bonding electrons. The higher energy states are commonly known as anti-bonding orbitals. The anti-bonding orbitals associated with sigma and pi bonds are called sigma star and pi star orbitals respectively. However, there are no anti-bonding orbitals associated with n, that is the non-bonding electrons, because they do not form bonds. The next chart will show you essentially how the energy is increasing for these various types of electrons and how the anti-bonding orbitals are placed. Now, first and the foremost thing that one should understand is that these electrons, how facile it is to excite a sigma bond, what is the kind of energy difference for a sigma electron to go to sigma star orbital, or whether it is easy for a pi electron to go to pi star, or is it easy for the n electron to go to either pi star or sigma star. So, these are various transformations that are possible when the light is absorbed. Now, light is bringing it is an electromagnetic radiation, has a certain amount of energy associated with it. Now, when that energy is actually compatible with the energy requirement of the molecule for the excitation, only then the light will be absorbed. First thing that has to be understood very clearly, the light has to have a matching wavelength of the wavelength that would be actually required for the excitation. A wavelength of light is associated with a certain amount of energy, and these amounts of energies are always quantized. So, when it comes with its energy, that energy is what actually causes the excitation of the electron. So, if we try to look at this chart, you will see that this is the order of increasing energy levels of various orbitals. You see, bonding sigma is the lowest, bonding pi is above that, non-bonding or lone pair electrons are above that, pi star is further above that, and sigma star is. So, if one has to promote an electron from sigma to sigma star, it would require the highest amount of energy. If one has to promote from pi to pi star, that would require certain amount of energy, and the most facile would be promotion of a lone pair electron to the pi star orbital instead of sigma star. So, these are the kind of energy requirements, and when the energy requirements are matching with the wavelength that is incident on the compound, that the transaction of the or the movement of the electron can be facilitated. It is not that any electron can move to any situation. So, the electronic transition can occur by the absorption of either UV light or visible radiation, because that is what matches the range. Although transitions are possible, only the following types are allowed. Although it is possible to promote a sigma to sigma star or a pi to sigma star, but you will see that only n to sigma star and n to pi star and pi to pi star are the allowed transitions. A sigma to sigma star transition takes place when a bonding electron is excited to an antibonding orbital as sigma star. This type of transition requires very large amount of energy, as sigma electrons are very tightly bound. Hence, the compound like saturated hydrocarbons which do not have any pi or sigma electrons may undergo only sigma to sigma star transitions. However, these transitions do not take place by absorbing ordinary ultraviolet region, and therefore, ethane absorbs at 135 micromu. So, you see that it has a wavelength requirement which is even below ultraviolet region, and therefore, these transactions require very high energy, and they are colorless compounds altogether. So, if one tries to look at these transformations, you will also understand that what is allowed is n to pi star and pi to pi star, and n to pi star. Now, if you try to correlate with the auxochrome and the chromophores, you will see that pi to pi star is a typical case of using the chromophoric electrons. Chromophores are pi electron containing groups. So, it is the excitation Now, the modern theory does not completely violate the Witt's theory, because it is also based on chromophore and auxochrome, but the more plausible explanation in terms of electronic excitation, and the electronic excitation is related to the incident light. When the incident light is matching completely with its energy content, which is required for these pi to pi star or n to pi star transition, then only the colored compound will absorb and will transmit the complementary color. So, now by now you may have understood that the Witt's theory still holds good and can be related to the modern theory of these pi to pi star and n to pi star transaction of electronic excitation. It is very important that you have to understand in the perspective of the structural constitution and the structural constitution containing the chromophore and the auxochrome, how they participate in these transactions when the light is incident, and the matching of the light with these transactions. Giving you an example of ethane. Why ethane is not a colored molecule? Because it is not even falling, it requires an energy which is much higher than the energy content of the UV light or the visible light. Therefore, it cannot be seen as a colored molecule. So, for a molecule to be identified as a colored molecule with the help of the incident light, it is important that it should have chromophore, and the chromophore bears the electrons which need excitation from the pi to pi star or n to pi star. So, auxochromes, chromophores, light and constitution, they all play a very important role and go hand in hand. Otherwise, one will not be able to explain why a certain chemical compound is colored, why it is categorized as a dye, and its identification as a dye molecule comes from its structure. We just took an overview of various types of structures, the anthraquinoid dyes, the indigoid dyes, the dihydropyran dyes, the anthraquinone dyes. These structures all have chromophores, all have auxochromes, and therefore, they are able to take up the light from the visible region and excite their electrons from pi to pi star, n to pi star, thereby showing that they are colored molecules.